And now we are going to explain how insertions and deletions are penalized in sequence alignment. Previously, we just discussed about penalizations, but the left alignment and the right alignment in our model will score the same, but they should not. So we will use a different penalization when we open a gap, like here, and when we extend the gap, like here. So we call affine gap penalty for a gap of length k, sigma, that is the gap opening penalty, plus epsilon multiplied by the gap length minus 1. And clearly, sigma, the opening gap penalty, should be higher than epsilon, the gap extension penalty. Now, we wish to check how to model affine gap penalty by long edges. Up to now, we use only a single. This is a double gap. And up to now, we consider a double gap as twice the value of the gap. But in reality, we could use a different value, and it is a single arc of a different value. Now, we wish to build a Manhattan with affine gap penalty. As you can see, I have horizontal and vertical lines, and I'm going to increase of n power 3 the number of edges to the graph. To reduce the number of edges, remember that nodes are less computationally hard than edges. So we are going to divide the graph in 3 levels. A bottom level, well, we have only the insertion. A middle level where we have matches and mismatches. And a upper level where we have deletions. And we wish to emulate this path in the 3-level Manhattan. The first arc is on the middle level. After, I'm going to move to the second level because it is the south one, and I'm going to draw a vertical arc of value epsilon, and I'm here. I'm going to have a second vertical arc now. Here. And I'm going to come back. This is a red one. That was this one. After, here I'm going to have a blue one that is going here. I'm going to cross with an epsilon cost, and this one had a sigma cost. My apologies because before I was wrong. The first arc is from this point to this point, and the second arc from this point to this point. Okay? I come back to this point because this is the diagonal one, and I go to the end. Now, I show you what is called a three-level Manhattan graph.